Hello everyone and welcome to today's webinar, fifth one in the series organized by Manav Human Atlas Initiative. My name is Jyotsna and I'll be your moderator for today's session, the future research scientist in the age of AI and big data. Scientific knowledge and technology are advancing exponentially with breakthrough research being published every minute, refining our understanding of who we are, where we come from, what it takes to attain good health, and how we can advance the human-machine relationship. Is it really possible to harness this explosion of knowledge with our traditional research methods? With that preface, what skills will future researchers need to acquire? While it is evident that research scientists will emerge as an exciting career option for students of science, particularly in life sciences. This webinar will cover the emerging possibilities at the confluence of biomedical research and technology's ability to rapidly search and synthesize incredible amounts of information in big data sets using artificial intelligence. To tell you more about this, we have with us Dr. Ujjwal Rao. Dr. Rao, presently a senior clinical specialist in integrated decision support solutions in ELSEVIER, is an emergency physician and a clinical informaticist. He has been designing world-class clinical decision support systems with evidence-based information solutions for healthcare. He is a physician executive and quality system specialist, adept at healthcare information technology and artificial intelligence in medicine. He is a quality consultant with the United Nations and an assessor on the panel of Quality Council of India for the NABH. Dr. Rao is also working with several government and private sector organizations in the healthcare delivery, clinical research, health IT, and data science ecosystems across the world. Now, before we start on the session, a quick announcement. If you have a question for our speaker, please be sure to send it only through the Q&A tab at the bottom of your player. The questions will be taken at the end of the webinar during a dedicated question and answer session. Also, to make this session interactive, Dr. Rao will be asking you some questions which you can answer via poll. The poll will be only visible on Zoom and will not be available for our viewers on Facebook. Now, without further ado, we will turn the time over to Dr. Rao. Dr. Rao, over to you.
Thank you, Dr. Jyotsna. Good afternoon, friends, and thank you to the Manav team for inviting me over for this, in one of its kind of webinar in the series of data science webinars. And I must thank, the organizing team, NCCS, ICER, Persistent Systems, as well as the Department of Biotechnology under the Government of India for having such webinars for students of science and doctoral scholars. I think it's the need of the hour. And when I was invited to speak on the topic that you see on your screen now, I was essentially in two minds. I had two options. Either I could speak about AI and big data from its technological implications, go into the depths of these frontier technologies, or the other option was to actually discuss some of the experiences that I've had personally as a researcher, as a clinician, and I've seen various facets of healthcare, and to share with you students and scientists what those experiences could imply in terms of how these various fields actually converge. So I stuck with the option 2, and I hope that's well worth your time today. So let me start off by actually talking about my story, life story as a researcher. So when back in the days when I was actually studying medicine, I thought maybe I could research whatever I want as a medical student. You have that gusto, the zeal, of youth, and actually the kind of perspective you have on science and healthcare. You want to change the world, and you have that energy to do so. That somehow kind of, once I started doing my masters, and I mastered in health systems research and hospital management and medical law as well, I realized that that aspect gets kind of further truncated, and you realize that the research that one can actually do is more dependent on what your professor wants. And that further, once you actually start looking at the time when I started to do my PhD, and it was a tough one, because I was doing a PhD, a medical student doing a PhD from an institution like BITS Pilani. So it's tough, when you have a doctoral advisory committee full of technocrats. So that was something where I realized that the constraints in terms of having DAC from a technology institution, so the research further takes a different direction, and your thought starts to change as well. And then further, I mean, cut down to the current day and age. And I obviously am not this old. There's a while to go. But in my postdoctoral phase, I'm doing research on cognitive technologies, artificial intelligence, and data analytics. And that's something which I feel is again kind of constrained in terms of the way funds flow in. I mean, you can't be doing research theoretically. There has to be some translation of this research as well. So I mean, unless time runs out and I have the same kind of the desire that I would want to research whatever I want, going back to my medical student days, before I ultimately have to either research in peace or rest in peace. So that was, I mean, obviously that's just to get us started. But on a more serious note, there are obviously quite a few challenges with research, specifically in terms of life sciences research, and more so with the status in India. And if you look at these factors multidimensionally, the first being organizational factors, things like funding, infrastructure, technology. Then further looking at policy related factors. One thing specifically from at least life sciences point of view is the regulatory requirements for research, and that I think is critical in terms of having a research that is validated and is approved, and for you to be able to go through with that, and then further get onto a stage where you're able to translate those research findings into practice. More so in my field in clinical medicine, that is very critical in terms of things like drugs and vaccines, and things that we are currently actually confronted with the ongoing pandemic. Then there are the ethical factors, and many of us realize that at least in clinical research, there is a lot of preclinical studies which involves testing on animals, and that's something which we've been trying very hard to see how technology can enable animal studies to be obviated. And that's another factor that kind of offsets the desire to be a researcher, specifically in the clinical sciences field. And also there's the other aspect which my statistical friends would appreciate, is something we call ascertainment bias, whereby as a researcher I have a certain view and conviction about a certain aspect, and I go out and look for data to actually kind of support the hypothesis that I have in my mind, but I've already proven the hypothesis even before the research has begun. That's the ascertainment bias. So these are some of the ethical factors that kind of dissuade one from pursuing a research career as such. And then finally there are the individual factors. How much interest do you actually have to be a researcher, given the amount of time it requires, long hours, sometimes going to decades in terms of the seeing an output as such. It generally doesn't motivate one to take up research, because then you want to see the result of what you're doing immediately, and that's something that unfortunately isn't the case with research sciences. And finally, there's the financial aspects too, right? I mean, obviously it's not the highest paying job to be a research assistant or a researcher per se, And that's something which I think also doesn't incline one towards taking up this as a career as such. And I thought I would discuss these aspects, threadbare, so that we are, kind of really cognizant of the actual situation. And this is pretty much reflected in the way our research workforce is in India as well. If you look at this metric, which we call the researchers per 10,000 labor force, you'll see that India has 4 researchers per 10,000 labor force, compared to countries like China has 18, Russia has 58, and the UK and the US have 79 researchers per 10,000. And mind you, their populations are probably just fractions of what it is in India. So you realize the real dearth. So we have just about 2 lakh researchers. 14% of them are female. So there's a kind of gender inequality as well as far as research is concerned. So there's definitely, there's reasons and there is need for more researchers to join the research workforce as such. And that's when I realize that folks such as yourself, who've taken up science as a discipline, and most of you are BSc, MSc, and some PhD students. And I realize there are some scientists on the webinar today as well. But this is the actual status, So given this, and this is my great friend, the crusty scientist, who I follow on Twitter. Quite a few interesting tweets from his side. So the question then is, right now amongst you, who actually wants to be a researcher? And then Dr. Jyotsna did mention about the polls. So I might just launch this poll, and what you'll see on your screen right now is a question which says, do you want to be a research scientist? And what I would encourage you to do is, give a response to me, either whether it's yes, no, whether you're sure or not sure, right? So we get a good sense of, what the actual, inclination towards research is. And I realize that there are some of you who are already researchers and PhD students, and there's already scientists as well. So you could obviously write yes, unless you realize that you were in the wrong field altogether. I mean, then feel free to say no as such. So yeah, I'm getting quite a few responses, and I think we have about 355 participants right now. So yeah, I think I've about got the entire set of. I'm going to give this a while until you complete this poll as such. So 68% have voted so far, 69. We've gone up to 250. I'm going to stop somewhere around 350 or so, because those are the eventual number of participants here. So I'm just going to give this a couple of seconds while you finish this, yeah? All right, so we've got about 285 responses out of about 360 participants. So that's almost an 80% vote percentage, and it's still increasing. And yeah, so I'm going to just end this poll once we hit 300, because I realize 19% of you are either not able to vote, or probably some technical difficulties. Okay, so I think we've gone up to 293. So I'm going to end this poll now, and I'm going to share the results with you. I hope you can see the screen now. So you see 74%, so almost 75% of you have answered yes. 6% say no, and 21% of you are not sure. So that's a figure I think is pretty representative of the way this is Actually, it's kind of expected as well. I realized that we would have a significant percentage of people who actually want to be research scientists. See if we can kind of change those, move the not sure ones into yes. Yeah. So I'm going to move on now and talk about the future of global research. So there was a study in which was originally based on a British Medical Journal article, which talked about the future of global research on two parameters. And if you see the way this matrix is, you've got on the x-axis the funding landscape going from consolidated to fragmented, and you've got technology adoption on the y-axis going from it's either hindered going up to transformative, right? So if you look at the way this is, and I'm pointing towards the bottom right quadrant, this is neighborhood science, right, where technology is hindered and the funding landscape is fragmented. And this is pretty much the status we are in right now. And we realize that although we are quite connected with the global research community, but the actual amount of interdisciplinary research is still constrained. So we would want to associate with people we know as opposed to their research interest as such, and that's what we call neighborhood science. Now, once we start changing that, and if you improve the funding landscape and consolidate it further, what you'll see is what we call a post-West power shift, where research is moving from the Western predominance to countries like China and India, where we become powerhouses of research. And then once you start changing the technology landscape, and it starts to move from hindered to transformative, and what you see on your top right, that quadrant is what we call the sustainable health goal, where you would have probably heard of the Sustainable Development Goals, SDG, and SDG 3 more so in health. And that's what we will be able to achieve by the year 2030. That's the global timeline to achieve SDGs. And this would be possible with the help of technologies like artificial intelligence and our ability to mine huge amounts of data, and be able to connect with interdisciplinary teams, and which is more focused and directed research. Then when you move to the top left, where technology is transformative and the funding landscape is also completely consolidated, where funding moves from agencies like CDC, and for that matter BIRAC from DBT. It moves to companies, tech giants who are able to fund research, and that's when, and also enable future cognitive technologies to take up the mundane tasks involved in research, right? So that's when we start to get to what we call techtopia, which is a combination of technology and utopia, where majority of the actual work will be taken up by machines, and we'll be able to focus on the more emotional and aspects of research to do with things like ethics, equity, empathy, and excellence in the research output as such. So it seems that it's a simplistic matrix, but it has got a lot of sense to it in terms of how it pans out as such. Moving on, I think the key to all of this is knowledge, right? I mean, at the heart of it all is knowledge. So when you realize that all of these technologies, when bereft of knowledge, have no actual meaningful output as such. And that's when, if you look at the situation currently, before Valentine's Day of this year, the world didn't know a term called COVID-19, right? And after 3 months, you realize that there are almost 21,396 articles on COVID-19. And this is specifically in clinical sciences alone. So if you look at overall life sciences, this figure is likely to be in the hundreds of thousands. And this is from our solution, Clinical Key, which is like the globally benchmarked clinical reference solution. So you see the amount of articles that have been published, systematic reviews, and you see clinical trials, almost 1,700 clinical trials which are ongoing right now in COVID-19. So you realize that knowledge, within 3 months has actually, come up to a stage where we've got tens of thousands of articles on COVID alone. And that's what, presents us with what we call the knowledge dilemma, right? The one is that the two aspects of the knowledge dilemma, and I keep speaking about this quite frequently in my talks. There's two parameters, right? One is how long does it take for knowledge to come from theory into practice, which is called diffusion of medical knowledge, and the other is doubling of medical knowledge, right? And so as such, in terms of diffusion, and if you allow me, I'm going to check. Usually I ask people what if they know this answer, but how long does it take for knowledge to come from theory into practice, right? What is the amount of time it takes for knowledge to diffuse into practice? So I'm going to again launch this poll and see whether what is your sense on the diffusion time. And you can, just similar to the way you answered previously, please start, giving me an answer of what you think is the diffusion time. Good. This time we've gone up to 230 rather quickly, and almost 47% of you seem to be thinking that it takes about 7 years for knowledge to diffuse into practice. So in the interest of time, I'm going to end this poll in another 10 seconds. 20% of you think that it's 17 years, 26% of you think it's 3.5 years, and 7% of you think that it's 73 days. Okay, good. So I'm going to share these results now. And if you see 7 years, 48% of you answered that it takes about 7 years. Now, traditionally, when we look at randomized controlled trials and systematic reviews and such like, and there's an article which you see down below. So this has been known as the magical figure, right? It takes about 17 years, and 17 years is the correct answer, by the way, for knowledge to diffuse into practice. And that's an awfully long time, isn't it? But you realize that with the way that COVID has actually changed, the scenario these days. We are seeing rapid diffusion of medical knowledge, and I promise I'll come back to this aspect a while later. The other aspect is doubling of medical knowledge, right? It's basically looking at how long does it take for knowledge to go from X to 2X. So, for example, if we have the entire amount of medical knowledge today, say for instance, say 12 exabytes, how long will it take for it to become 24 exabytes? So I'm going to launch this one again, and let's see what answers do you have for this one. Great, you seem to be getting the hang of this. So we're almost up to 265 and increasing, going up to 300 already. Interesting. So there's also wisdom in the fact that you if you answer the same option in multiple questions, the likelihood of you getting the right answer is manifold. So this MCQ strategy, unfortunately, it didn't work for many back in my med school days. So I see a lot of you answering 7 years to take the average out. Well, so I'm going to end this poll right now, and I'm going to tell you that if you look at it temporally. So if you look at this figure, back in 1950, knowledge used to double at a rate of 50 years. Then, cut to, 1980, it became 7 years. In 2010, that rate was 3.5 years. But in 2020, that rate is 73 days. So those of you who have answered 73 days, you are correct in the present time. The rest of you would have been right, in 2010, 1980, and 1950 respectively. So that was interesting, wasn't it? Just to bring home the point that the amount of time it takes for knowledge, one, to diffuse into practice, and second, for it to double. And if you put these two aspects together, and you realize in life sciences that this is a critical piece where the amount of time it takes for knowledge to become practicable and is not aligned with the amount of knowledge that is being generated, and that creates a dilemma as such, and that's the reason why we have so many, at least in my field, what we call medical errors, errors of omission, errors of commission, and that's because we're not abreast of knowledge as such. So the question then is artificial intelligence really the rescue agent for us? And I would tend to think yes, because predominantly, and if you look at your screen in three parts, on the left you see all the inputs as such, and the middle is the processing, and the right is the output, input, processing, output. So here you see the amount of data that exists within things like nucleic acids, so DNA, RNA, nitrogen base pairs, and then the genomic sequences, proteins as such, and also preclinical data sets. And then you move on to the actual, and this is an example of a clinical trial which gives an indication of how research is. And in clinical trial, efficacy and adverse events, there's a lot of information that's generated from things what we call serious adverse event reports. And there's also this real world data and evidence coming out from things like fitness trackers and retinal scans and medical images, and also the amount of evidence-based information coming from peer-reviewed journals and articles, and also the EHR data, which is patient health records as such. So if you are able to mine all of that and process it through advanced technologies, think computational analyses like computer vision, feature selection, and various forms of neural networks and deep learning essentially, and then you're able to get into a state where you get things like the next generation of antibiotics. We've run out of our options as far as antibiotics is concerned, and personalized medicine, which is tailor-made to each individual patient as such. And then you're able to also make predictive models about one is the clinical trial efficiency and effectiveness, and shorter cycle development times, and also novel digital endpoints. Like nowadays we talk of virtual clinical trials where patients don't have to follow up at the hospital as such. And these are all possible with the advancements in technology, and specifically artificial intelligence based technologies. So when we at Elsevier started to actually research the whole field of AI, what we did was we started to use AI to research AI. So we developed an AI technology to look at publications in the field of artificial intelligence as such. So what we realized is that all of there were, I think, about 6 lakh articles, and all of them in the last, I think, 9 or 10 years address these major topic clusters, which you see on your screen right now. Things like machine learning, neural networks, computer vision, and the rest of the fuzzy systems, search optimization, planning, and decision making. I don't want to get into the depths of it. My intention, behind this was to actually give you a sense of how these key terms are actually related in terms of the interdisciplinary research within AI as such. And if you go further into this, you start to see what we call a chord graph, and this is what you see. This is a chord graph. So one thing that you're probably familiar with is natural language processing, right? So if I look at NLP, and you see that on your bottom, you start to see semantics. You start to see things to do with knowledge representation, word disambiguation, and natural language understanding and machine translation and such like. So if you look at the patterns as such, and there is a lot of connectivity between various keywords and key terms, and you realize that this is all an interconnected field, and the research as such doesn't happen in silos. So that was the way we actually researched and created this chord diagram. But if you look at the key terms as such with these, and these are 600,000 scholarly publications, and you'll be able to see that there were certain publications which were AI publications, and there was the light blue ones are non-AI publications. And you had terms which were high ranked, mid ranked, and low ranked. So when you see the high ranked terms, those have to do with the depth of technology of AI itself, things like backpropagation neural network, which finds a mention about 8,000 times in AI publications, whereas only 70 times in non-AI publications. In the mid-ranked ones, you see applications, things like self-driving cars, autonomous cars, 2,000 odd times in AI publications, and 1,400 times in non-AI publications. And you see low-ranked terms, these are more in the sense of theoretical sciences. For example, non-locality is a quantum mechanics theoretical concept, which means that there is no absolute space and there is no absolute distance as such. This is all non-locality. So you see in AI publications, it was mentioned only 19 times, whereas in non-AI publications, it was about 3,700 times. So you realize that, the amount of, work that's been going on in AI research and the way it moves from, the actual core technology of it to applications, and then to start to answer questions that we've had no answers for so far, and that's the potential of AI, right? So the question is, where are we? Where does India stand in this whole landscape of AI research as such? So this was a pleasant surprise to me as well, that India was ranked third, in the entire in the world, and this was 2009 to 18. This was in the 9 years we published about 40,000 odd articles in to do with artificial intelligence. And if you look at this research further, you saw that India was. I'm going to select India over here, and once you do that, you see this is our rank. We are ranked third, and this was behind, obviously, China is number one on AI with 127,000 articles, followed by the United States. But interestingly, if you look at a metric called FWCI, Field Weighted Citation Impact, which essentially gives you a sense of how many people have cited your article, as opposed to what was the expected citation for a similar article, a similar journal. So India's rank is 75th, and you see number one is Hong Kong. And this gives a sense of, the kind of quality of research as such, where there's a lot of work to do as such, and that's another revelation that we had. And if you compare that with the global overall research performance in life sciences as such, and this is, a sense of you get FWCI of about 1, and we had about 7.8 million authors for those 9 years, 5.3 million, scholarly output in terms of the number of articles, and 5.3 citations per publication. And this is done by an application called SciVal, which is able to instantly analyze multiple, big data sets and come out with research performance assessment. This is used by big organizations to come up with evidence-based research strategies. So the top 5 research topics that came through were to do with immunotherapy, genomics, mostly around genomics and cancer. And in India, you see that we had only about 237,000, which is 2.3 lakh articles, and our impact was just 0.74 with about 3.3 lakh authors. But interestingly, the top 5 research topics ranged from things like nanoparticles, which was to do with drug delivery system and MRI and ophthalmology. And interestingly, it included things like data mining and disease predictive models as well. So this was a good indication in terms of the future research direction for India. And I talked about SDG, and I promised I'd come back to this. If you look at the SDG 3 and the amount of research that we've published on the Sustainable Development Goal for health, and this is global, obviously, and we've got about 2.7 million articles. Remember, the global overall output was about 5.4. So you can see 50% of that is directed towards achieving SDG 3, which is great news. And if you look at the key terms in this word cloud, which again, I think Saival creates automatically in a couple of seconds, you see that mostly it's centered around things like cancer, therapeutics, HIV, evaluation studies, RCTs, etc. But again, India's rank on this is 9 with about 100,000 articles published on SDG. United States is ranked first. And I think we are almost, I think, ninth in the amount of COVID patients as well, which I think is going to rise pretty soon as such in terms of the way the pandemic is ongoing. But that's obviously a lateral point. But there is certainly a lot of work that needs to be done. Now, the question then is, we've got all of these articles and this research and this knowledge as such. How do we use machine learning for actionable knowledge, right? And I'm gonna, I promised you I won't get too deep into the tech as such. I'm gonna just skim through these slides. So the first part is being able to take all these knowledge sets, and data silos that we have, ingest them, and this is another solution called Intellect, which is able to do that. Ingest that into a form which is basically breaks down all of the silos and digests all of the entire multiple data sets, and then enriches these into specific, data points, separating them as compounds, drugs, targets, etc. So, for example, you see this hydrocarbon, this nitrogen-containing hydrocarbon, which is part of a drug called osimertinib, which is again an EGFR gene target. It's a gene target which causes a type of cancer in the lungs. And you see, once you start making these connections by annotating this using taxonomies and ontologies, you're able to build those relationships, right? Moving from hydrocarbons to the drug itself and how the gene target can be used, and you can make those inferences as a potential drug for lung cancer. So that's what one can do. But at the heart of this, if you see, is natural language processing. And I know that you've gone through a session on NLP, so I'm not going to get into the depths of this. But Elsevier has created an NLP tool, and we are able to do text mining on all of the articles that we publish, and we've made these available on the CORD19 dataset as well. So what you see is I've used the key term SARS-CoV, and on the left you have these filters like the receptors, ACE2, the virus spike protein, endopeptidase, etc., interleukin-6. So I can switch those on and off to include or exclude those. And once I get into the actual article, it gives me a sense of what the various concepts and entities are, where the proteins lie, what are diseases, organisms, cell lines, etc. So you're able to, kind of automatically annotate and tag all of these concepts using taxonomy we call EMET, which is also part of MBase, which is a biomedical database which uses the taxonomy called M-tree. So essentially, the idea is that you're able to use these taxonomies to build a knowledge graph. So this is one knowledge graph we built for COVID-19. So what you see, the blue nodes are diseases, MERS and SARS. The orange nodes are proteins, and the brown nodes are drugs. So you're able to find out which drug is a downregulator or an upregulator of a certain protein, which then actually expresses the kind of pathogen and is able to actually create that scenario whereby the disease is expressed as such. So once you take these, and I explained in that schematic earlier about the ontologies, and you build a knowledge graph, then you're able to build these nodes, and there is a Yen's algorithm called Yen's K shortest path, and you find the shortest path between two specific nodes, and then find out, and gives you insights that you probably may not have had. For example, there's this article which says that anti-A antibodies, meaning the blood group A antibody, is probably has a protective effect against the SARS-CoV because it inhibits the protein expression for on the ACE2 receptor as such. And then there's this about tuberculosis, that patients with tuberculosis probably have a higher risk of getting a severe form of ARDS, acute respiratory distress syndrome, in COVID. And then again, you apply machine learning on this, and you're able to make out which are the upregulators, downregulators of SARS and MERS, and a concept called autophagy, where so green is good and red is bad. So you see things like drugs like doxorubicin is probably got a high significant, statistically significant upregulation of autophagy. So it might be a good candidate as a treatment agent. And so you start getting these machine-based insights. Another aspect, and we touched upon this in the challenges as such, is for the ability, to do preclinical studies in animals, right? And those of you who are animal lovers, don't really, encourage these animal testing. So one of our Elsevier members, Dr. Matthew Clark, conducted this study where he put all these adverse event reports, and for 70 years, all of the submission that comes to US FDA, and put that through big data analysis, and was able to come out with unprecedented insights, in terms of what drugs cause toxicity in animals. Like, for example, a thing called QT prolongation on the ECG. Certain drugs, you can cause sudden cardiac death, for example. And QT prolongation is a side effect of hydroxychloroquine as well. And certain drugs cause arrhythmias in dogs as well. So you don't need to give that drug to the animal as such. You've got all of this data set, and you can actually simulate this in what we call an in silico trial. So those are some of the applications of big data and AI as such. But the question still remains. I mean, have we been able to surpass this whole 17-year barrier for knowledge to come to practice? Well, the model as such, when we look at something called translational research, moving from bench to bedside, where you're able to take all of these preclinical studies and put them into phase 1 and 2 trials in tens and hundreds of patients, and then move it to the bedside in phase 3 trials into thousands of patients, and then bring it to practice. This traditionally, which was 17 years, is now getting transformed with the use of practice-based research, where you're able to generate evidence from all the treatments that doctors are providing right now, and use that as real-world evidence to really exponentially speed up the process of knowledge diffusion. And then you're able to translate it into patients and to practice as well. So in the case of COVID, this has come down from like 17 years to 17 days. And some of you have, probably known of cases where, for example, I read an article in the morning about a certain drug which was useful in a patient, and I have a patient who's, really sick on a ventilator. I might just try it on compassionate grounds. So this is what we call the research practice hyperloop, and that's something which has become very relevant in COVID-19. And I think post-COVID, we need to maintain the same kind of momentum as far as research and practice is concerned, right? But one quick word of caution, with artificial intelligence. So we've talked about all of these applications, and it looks all, hunky-dory. But there's also this aspect of artificial intelligence which we need to, tread carefully on. For example, when I was in my earlier days, when I was learning natural language processing, so my professor at Columbia University gave us this example of something called so when the earlier NLP algorithms were actually asked to translate something like out of sight, out of mind. You say that, right? Out of sight is out of mind. And when they put that into an NLP algorithm, the output was invisible idiot. So obviously we've come a long way since then, and NLP has kind of got a sense of the semantic output as such. Then there's this other example of a study which was published in Nature to do with skin lesions, potentially cancerous skin lesions. So when they used a deep neural network algorithm, so it was surprisingly very accurate. And and it's like you're not able to find out how it is reasoned so, right? So when they looked at the actual algorithm, it realized that every image that had a scale, it started to classify as a malignant lesion, and that's the reason why it was able to accurately diagnose cases and not by the actual lesion itself. So you realize that AI is unpredictable in that way. And then there's also this algorithm we call reinforcement learning, right? So this is a game called Coast Runner, and they developed an algorithm to actually play this game. And reinforcement learning works on the principle of getting rewards. So the more points it gets, the better it is performing its things. And so the game realized that if in this loop it's able to get maximum points, so the game didn't go any further from there. So the deep reinforcement learning algorithm kept going on in a loop for eternity. So again, a case in point in terms of the caution we need to take with AI. And obviously, I think you all are future data scientists. It's important to realize that you need to have fail-safe mechanisms. So, for example, the laws of robotics that Asimov came up with in the 1950s, that a robot will not injure a human. And number two is the robot must obey the human orders unless it is in contravention of rule number one. And rule number three is the robot must protect its own existence as long as it's not in contravention of number one and two. So we need to have some simple, elegant laws to make sure that AI works safely for us. And it's generally, it needs to be looked upon as a general purpose technology, right? It's like the internet or electricity. It's not an end in itself. And for that, I think it needs to move from the concept of being, something like a black box where you saw that you don't know why the algorithm is, looking at skin lesions, for example, and you realize much later that it's because of the scale. So that's the black box. You can't see inside, and it's very machine centered. And we need to transform those technologies to what I like to call the glass box kind of AI with a human in the loop, which is IA, intelligence augmentation, as opposed to AI. And that's the key. And I think that's the future direction that we need to take. And as far as professions of the future are concerned, you'll be surprised, and I was surprised to see, professions like drone runner and medical clown, and these exist today. There's a post called chief belief officer, chief dreamer, an ethical health data hacker. And another profession I think is on the horizon is applied research data scientist. And I've put applied and data within brackets because those are implicit for a research scientist, meaning going from having these skills of your domain, pharmacy, biotechnology, etc., coupled with skills in mathematics and computer science. And at the cusp of these overlaps, you see data processing, the ability to do statistical research, machine learning. I think that's the future direction of a research scientist, whereby every research scientist implicitly will be a data scientist and will also be required to apply those. So that is the kind of future that you can look at. And the salaries I think now are just enormous in terms of the way the science is folding out, and the benefits are also quite evident, and the skills in terms of programming, etc. Mind you, you don't need to be a programmer to be a data scientist as such, right? But you need to have a sense of the data schemas, what data will be put to use for what kind of output as such. So having that sense, for the actual application, I think that is the critical piece. Yeah. And again, as far as knowledge is concerned, the more you know that you don't know. That's what Aristotle said. And if you think of research, if we knew what it was we were doing, it would not be called research in the first place, would it? And that's what Einstein said. And I think there's a lot that we still need to know, and there's a lot that is yet unknown, I think. And I think Manav is an excellent example of future research. It exemplifies all of these fields. So from what I hear, 5 million articles are being kind of annotated, and then they're creating an actual atlas of the human, which goes from macro to micro, come up with unprecedented insights in terms of diseases and how to treat those kind of diseases. So I'm sure most of you are already part of the community, but if you aren't, I'd encourage you to sign up with Manav and be part of this community as such. So again, so my question then is, who wants to be a research scientist? And the man that I am from science, I love to do pre and post. So I'd like to know, who has had a change in mind in the last 45 minutes or so. If you can kindly tell me your opinion right now, we highly encourage. In the interest of time, I'm gonna close this poll rather quickly. Okay, so I think we've almost reached up to quorum. Almost 75% of you voted. Brilliant. All right. So good news here is we've got 12% who are not sure. So that's a 15% increment in terms of, the yes versus not sure. So we moved from, I think, 75 to 87% and moved those, I think, about 9 or 10% into the yes category. So I think this was, well worth the time. And obviously, I foresee that, at least a few of you will take up data science as an inherent part of the way you take research as part of your career as you go forth. And at this stage, just like to quickly tell you a bit about what Elsevier does from the health perspective. We are a team of almost 7,500 people. We've been around for 193 years. You would have heard of titles like Grey's Anatomy, Lancet, and Cell. But now we are increasingly using these knowledge solutions to integrate this with electronic health records to improve patient outcomes at the point of care using predictive models and machine learning. On the life sciences side, you would have seen a glimpse of what we do with data in research and development, get it analytics ready and harmonize that data and provide curated scientific information. And obviously there's not much time to talk about these products, but please feel free to reach out to me, and I'll make sure that you get the right answers as far as your products and any further questions are concerned. And I think we have about at least 10 or 12 minutes to answer any further questions. Dr. Jyotsna, I apologize. I think I went 5 or 6 minutes ahead of the scheduled time.
No, sir. It was an immensely insightful session, I would say. And I mean, I have received a lot of questions, and I need to ask these questions on behalf of our listeners. So I'll straight away move to the questions. So,
sure.
So there was an interesting question. I guess 4 or 5 listeners have asked this question. Is there any significance of programming language in biomedical and bioinformatics research? So they are asking that is there a particular language, programming language that we need to focus on to achieve?
Right. So this is obviously a topic for an entire session altogether. But just to answer that at the highest level, one is the programming machines, right? The other is being able to program knowledge into computable form. So for example, we work with a technology called a Redzo that's able to convert static guidelines into active guidelines, and that works on a language called Proforma, which is basically a guideline exchange format. So you'll find increasing number of programming languages which are specific to healthcare. And if you go to the the US or ONC, the Office of the National Coordinator for IT, you'll find the list of actual programming languages specific to healthcare. But yes, the idea is that you are able to program knowledge, which is called knowledge engineering, and then you're able to take that into a format which is in a format where you're able to build data schemas and models, for which you'll need things like Python and R and such like to build. So that's the integration. I think there are increasing number of integrations from these languages as well. where the traditional life sciences programming languages are now increasingly getting integrated with, big data platforms like, Apache Hadoop and, Spark and such like. And on the other hand, things like Python and such like, where you're able to build, scripts and write, machine learning algorithms essentially.
Yeah. Thank you for that answer. So the next question is, can you elaborate on the role and applicability of AI in precision medicine, especially in India, because we have ethical issues related to it? So this is a question a person is asked, who's from a similar field.
Interesting. No, that's a great question. And there's two aspects to this, right? One is when we started, thinking of medicine as such, and in our attempts to make sure that one size fits all does not, is not the way to go, especially with the increasing number of tumor markers and diagnostic tests, specifically in genetic tests in cancer, which now are finding a lot of space in the non-oncological space as well. You find a lot of more genetic markers specific to non-cancer type of diseases. And then you're able to, on the one hand, mine huge amounts of data, which comes from literature, because there are a lot of folks doing interdisciplinary research on cancer and other diseases related to genomics. So all of this genomic data, you're able to actually crunch further and be able to actually, like you saw in that schematic, annotate that data, so you're able to make out that this hydrocarbon containing nitrogen is able to target this gene, which is further expressing, a cancerous lesion in the lung, for example. So I think the implications are huge, and the amount of knowledge that we have right now is just, I think, in a very nascent phase, and this is likely to explode and change the entire paradigm of medicine, where we've been, all these decades we've been looking at just curative medicine, many a times given out of thumb rules, which people do it out of experience, but that's going to change heavily. And I think we've already started to see that in cancer, and soon we'll start to see that in other sciences like cardiology, neurosciences, things to do with treating or preventing Alzheimer's and Parkinson's and such like. So personalized medicine, I think, is a broad term, and but it, under its entire umbrella, it has many sciences which actually are going to change the entire face of healthcare as such. So I would encourage you to read up more about it, and if you're in an allied science that is related to one of these fields, I think that's an excellent career option as well.
Indeed, indeed. So there is one more question. There are actually 3-4 questions on a similar line. So the question is, how is the accuracy managed or indicated in an AI-related analysis? And what is the role of human intervention in this aspect? On the similar lines, there's a question which asks that what is something that we would miss out when we use only AI to analyze data? So
no, that's a very, I think, a pertinent question, and it's again going back to the coast runner and the algorithm that detects skin lesions. So although I'm a big enthusiast of machine intelligence, and I dabble with AI technologies, but I strongly believe that the need for a human in the loop is critical. And you realize that many of these algorithms, so although things that we call unsupervised learning, where the algorithm itself figures out patterns from the data and then is able to give you insights. So we've not reached up to a state where that accuracy can surpass humans as such, right? So humans have tremendous capabilities, and you realize that that artificial intelligence sometimes it might do tremendous tasks when it is put to that use specifically. For example, it's able to detect diabetic retinopathy out of retinal scans. But you realize that the AI has been trained to do only that, right? And you compare that ability to, say, my 3-year-old daughter, who's able to come out with unprecedented insights from me as well, from cartoons and such like. AI will take a lot of time to get to that state, where we say that it's a general purpose AI, and it's currently a very narrow spectrum that it's developing, but it's developing rather quickly. And I think our state of making it a general purpose technology is very much near on the horizon. But that being said, I think the time it might take for AI to for us to get to Techtopia is 2037 we thought was the state where we get to sustainable health. I think it would take further decades to get to a state where you're able to safely leave AI on its own, unless you land up with a situation like Skynet from the Judgment Day. Again, it's an opinion that one of my favorite authors, Professor Hawking, also kind of propounds. But yeah, I mean, it's always important to make sure that the AI is the slave and not the master.
Yes, indeed, sir. There is one more question. Actually, I also wanted to ask this question. How good, on the similar lines, of course, how good do you think that predictive analysis of an AI is? So, for example, if I want to say that, can AI be used to predict mutations in human genome? That could be disease causing. So, how reliable would that be?
So there's two aspects, right? So one was the actual ability to detect mutations, and the other is to predict whether those mutations actually will end up in a phenotype, meaning it will start expressing as an abnormality or a disorder or a disease. So the first part is already is being done as we speak. So huge amounts of genomic data, sequencing data is being put through what we call literally genetic algorithms, where they're able to get through the nitrogen base pairs and actually analyze those sequences and find out anomalies in them, and then try to simulate the output in terms of what those expressions might land up in. And that's happening right now. But if you talk about the ability to predict in a certain human based on the actual karyotype, for example, I wonder if you've seen the movie called Gattaca. It was an old movie when I was medicine, studying medicine. So that essentially showed that you just take your baby and you get a drop of blood, and you're able to say things like, okay, by the time you're 36, you'll end up with type 2 diabetes. At 64, you'll have Alzheimer's. That state is still story of fiction to me as such. But the ability to predict what specific point mutations can although the science is maturing as we speak.
So there is a general question from many of our listeners. They are asking about, implications or use of AI in different fields like autoimmune diseases, mutational research, herbal-based therapies, drug discovery, etc. I believe that's a topic for another day. But would you like to throw some light on,
Yeah, it is.
what?
So absolutely. I mean, I'll try to be succinct in my answer. So we've realized that the ability for the machines to do what humans probably take, so we are constrained by our senses, right? So how long does it take for me to read a 10-page article and then remember the concepts and then link it to another article and then come up with a hypothesis and then try and test that hypothesis. So this is heavy lifting, if you will, and if you give that to machines, they can do it in exponentially 10x 100x faster than humans can. And if you just take that concept, things like natural language processing, which we saw, and then try to actually put in further layers of application sciences, and then I think the potential in drug discovery, for example, you saw some of the simulations we did with the way the Ken's Y path. So you're able to create a network and then find out, for example, does an anti-A antibody work for SARS-CoV-2? That's something which nobody came up with. It's just from data set there is a possible hypothesis that comes out because the nodes are actually indicating as such, and then one can go and actually test that out. So the potential of this is immense, right from, herbal medication to drug development, chemical sciences, vaccines, for example, trying to simulate antibody responses within humans on an in silico basis. It's possible to do that. We have a technology called Pathway Studio where you're able to build in these knowledge graphs that you saw in my previous slides, and then query that using machine learning. So the technology is there, and I would encourage you to kind of start thinking about how that can be applied in your specific field, and then try to actually work backwards. What is the solution you need, and don't let the technology drive the actual application. Let the application find the technology that supports it. That would be my recommendation.
Yeah, that's indeed interesting. So one last question. I think I'll be asking this question on behalf of all my student friends here.
Sure.
So, what do you think is the future of this in India, especially in the present scenario that we are in right now? So, what do you think is the implementation of AI in India and in the field of research? So, what do you think is in
Yeah.
store for all of us?
So this one, I'd like to, mention about Niti Aayog, which is the, premier policy think tank of the country. And I've been working with, advisors like Mr. Alok Kumar and Anna Roy and, Dr. Vinod Paul and such people that I get the opportunity to speak with and, present to many times. And, there's this hashtag called AI for all. And if you read, and if you haven't already read this, there is a paper that Niti Aayog has published on the national strategy for artificial intelligence in India. And it encompasses fields like healthcare, smart cities, smart commuting, agriculture, things like trying to predict rains, trying to predict which is the optimum size, what is the distance between two seedlings, etc. And so many projects have actually been encouraged by Niti Aayog, and they've forged such partnerships, and we've been part of one of the AI projects as well. And we are doing a project for ASHA workers in remote regions in aspirational districts who take these AI based applications and start to screen for maternal and child disorders. And that's again based on a glass box kind of technology based on Indian guidelines as well. And this has the partnership of the UK Department for International Trade. And we realize that agencies such as Niti Aayog are encouraging the private sector to actually come up with such solutions, for problems that we've had for a long time. Things like reducing maternal mortality and such like. So I think with this government and agencies like Niti Aayog and the government and private sector coming so close together, I think the potential and the future for AI in India is tremendously bright. There are so many courses being run, both online and offline. We have institutions that are actually now, really entrenched in artificial intelligence. And I hear of talks of having a department of AI as well. So you could potentially see, for example, a minister for AI, things like that. It exists in I think in the Middle East, and China has got a structure around AI governance. So I think it's inevitable that we will have a very strong AI program driven top down, but actually growing bottom up organically. And that's where I think, my friends, you have tremendous opportunity and can contribute to the future of this country.
Yes, so we need to be on lookout for all these opportunities. I think government is providing, many of them. So I think people need to be, looking at these opportunities from both private and public sectors. So I think
Indeed.
we have covered most of the questions, not all, I would say, but due to lack of time, this is all that we could take up. So, sir, is there anything else you would want
Sure.
to cover before a wrap up? Like,
No, I just want to thank each one of you, and you've been extremely, enterprising in your responses in the polls as well. And, we would look forward to meeting all of you in person sometime soon. And hopefully this black cloud that we have of this pandemic should subside soon. But we still need to, kind of implement the lessons we've learned to make sure that we don't, tinker with Mother Nature too much to face a similar,
Yeah.
catastrophe in the future as such. So again, thank you, Dr. Jyotsna, the entire Manav
Thank
team,
you. Great.
PIs
Thank you, sir.
from NCCF, ICER, Persistent, and DBT, the Government of India. This was a tremendous privilege, and I look forward to seeing you again soon.
It was
Thank you.
an honor to have you, sir. Thank you. Thank you so much. We appreciate you being here. Now, before I end the session, I have a couple of quick announcements to make. So all the attendees, they are requested to submit their feedback through a feedback form, which our team will be sending over to you. So please make sure to provide your inputs, following which a certificate of participation will be awarded to you all. And regarding our next webinar on 28th May, we have Dr. Anguraj Sadanandam from Institute of Cancer Research, London, who will be delivering his talk on when and where to divide to conquer personalized medicine using systems and machine-based biology approaches. So these were the quick announcements I had to make, and thank you all for the session, and thank you all for joining us today, and I'll see you next time. Thank you so much.